Hello everyone, my name is Sheng-Feng. Today I'm going to present our work, boosting semi-supervised anomaly detection by contrasting synthetic images. Anomaly detection is the process that identifies the outliers, which are referred to as samples deviating from the normal distribution of a given dataset. And it has wide applications in general field of artificial intelligence, ranging from network intrusion detection to automatic manufacturing by robotics. Without loss of generality, the scenario of anomaly detection can be categorized into three classes. The first scenario is the supervised anomaly detection. It requires a training set to contain label instances for normal as well as anomaly classes. Well, the key difficulty of such a supervised scenario is a severe imbalance between the amount of inliers and outliers, in which typically the number of inliers is much larger than the number of outliers. And second scenario is the unsupervised anomaly detection. The training set contains both inliers and outliers, but without any supervision or labels. As such, unsupervised scenario focuses on learning to single out the outliers from the training set. It has typically become less generalizable to other data sets. The last scenario is the semi-supervised anomaly detection, which is exactly what we try to tackle in this paper. In the semi-supervised scenario, the training set contains only the inliers. Therefore, it's quite challenging to model the distribution of inliers without any assumption about outliers. And such scenario is also known as out of distribution detection. To be specific, the general idea of semi-supervised anomaly detection can be illustrated as this figure. At the training stage, we want to find a good representation that distinguishes inlier from anything else, such as outlier. However, we do not have any information about outliers, hence we can only try to learn a representation which does its best to model the inliers. At the test stage, the learned model will extract the representation of the test image and predict the outlier score for the test image based on their similarity with respect to the training set. Here comes the motivation of our proposed method. We stem from two popular approaches of anomaly detection. First, we learn generative procedure and modern distribution of inliers. For instance, the generative adversarial network composed of a generator and a discriminator is widely adopted nowadays. Second, adopting contrastive learning to learn the representation of inliers. It learns the feature representation while encouraging the sample of same class to be close, and the sample from different class to be far away in the feature space. While previous work independently used these two techniques, in this paper, we discovered the contrastive learning among the real sample and synthetic ones produced by the generative model is able to further improve the representation learning, thus benefiting the anomaly detection. Now, here comes the detailed intro of proposed method. First, the GAN learns to generate images from training data X. As our training set contains only inliers, this model only synthesizes the inliers. After we learn the generative model of inliers, we can apply the contrastive learning on real and synthesized inliers. Here we intro how the joint contrastive learning works among the real and synthesized inliers. For each sample, we generate multi-views using random crop and random color distortion, and we take these views as a positive pair, in which they are encouraged to attract each other in the feature space by the contrastive learning objective. However, in contrast to random crop or random color distortion, some transformations such as rotation will actually deteriorate the contrastive learning. Therefore, a previous work, CSI, proposed to treat the views under different rotation augmentation as a negative pair in the contrastive learning. Follow such idea, we generate 4 rotation augmentations for each image. And these views from different rotation augmentations will repel each other. Moreover, the views from the real sample and the views from a synthesized sample should repel each other as they are related to different samples. The feature extractor trained by using contrastive learning thus gets the information from both real and synthesized inliers. Moreover, in order to alleviate the model collapse problem, which is likely to appear in the typical GAN training, we additionally add the autoencoder framework into our generative model. Note that the decoder of the autoencoder and the GAN generator are sharing weights. For making the latent space of our generative model follow the normal distribution, we also include the latent discriminator to regularize the latent distribution of the autoencoder. With adding such autoencoder into our generative, the reconstructed sample produced by the autoencoder can be now also included into the contrastive learning. Given a real sample X and its reconstruction after going the autoencoder, there are two views under the same rotational augmentation are encouraged to close to each other. Moreover, when the contrastive learning is applied among the synthesized samples, as the synthesized samples are repelling each other, the generator is therefore encouraged to generate diverse samples, thus benefiting the overall learning of our generative model. Here we provide a visualization of the inliers, outliers, and the synthesized samples in the feature space, where we can see that the synthesized sample help to enrich the possible coverage of inliers, thus help the contrastive learning to better repel in the inliers from the outliers. In the test phase, we apply 4 rotation augmentations on each test sample. For each augmentation, we calculate its feature distance to the training samples. The feature distance is defined as the distance between the test sample and its nearest training sample. And the outlier score is the mean distance over 4 rotations. All results are summarized in this table. As you can see, our method shows better performance than the latest SOTA on several benchmarks, thus verifying our contribution on integrating generative model and contrastive learning in a unified framework for tackling the task of anomaly detection. Thank you for your listening.